Welcome to part 2 of our scheduling lecture. In this lecture, we're going to be looking at some more advanced schemes to scheduling. So before we looked at round robin, FIFO, shortest job first, and a couple optimizations for those. In this one, we're going to be looking at a few more advanced techniques or slightly different approaches to scheduling. Now, the first of these is our multi-level feedback queue, or MLFQ. Now, this is a scheduler that learns from the past to predict the future. So it's kind of cool. It's a more optimized technique. And its objective is to optimize the turnaround time by running shorter jobs first and minimize the response time without prior knowledge of job length. Okay, so how does it do that? Well, it incorporates a couple different rules. So MLFQ has a number of distinct queues, and each queue is assigned a different priority. So you can think of, with FIFO, there was one queue, like first in, first out, and that was all the jobs were put in this queue. Well, with MLFQ, think of that as having like multiple different queues, each with a different priority. And different jobs will go into these different queues, and the different queues will be processed at different times. So a better way of saying that is that we can look in the slides here is that a job that is ready to run is on a single queue. A job on a higher queue will be chosen to run first. Okay, and jobs within the same queue use round robin scheduling. So if you're in a higher priority queue, well, then you'll be run first. All the jobs in the same queue will utilize round robin. So this can be summarized in these two rules. So if priority of A, this is like job A or process A, is greater than priority of B, then A will run and B doesn't. If the priorities are the same between A and B run in round robin. So A will run for a time slice, then B will run for a time slice, then A, then B, as we saw in the round robin example. So how do we know what priority to set for a given process? Well, MLFQ varies the priority of a job based on its observed behavior. And an example of this observed behavior is as follows. A job that repeatedly relinquishes the CPU while waiting for input outputs, for that job, we want to keep its priority high. Okay, so if it's constantly giving up the CPU while waiting for input outputs, that is a job where we'll give its priority as being quite high. A job that uses the CPU intensively for long periods of time, we want to reduce that job's priority. So here we are saying that we should process processes which actively allow for other processes to be processed first, and those that intensively utilize the CPU for longer periods of time, we should process those last. So an example here is, given this list of priority queues like Q8 to 1, we have 4 different jobs. Job A and B are given the highest priority. So maybe this is one of those cases where they relinquish the CPU a lot of times, so they have a lot of input-output requests. And C and D are on priority queue 4 and 1. So how these will be processed is, well, A and B will be processed in a round robin first, then C, and then finally D will be processed or scheduled. Now, the priority of these processes aren't fixed, but they are changed periodically, and this is based upon our priority adjustment algorithm. And all this does is increase our number of rules from just those 2 to now 5. So rule 3 says that, well, when a job enters the system, it is placed at the highest priority. So initially, when a job is first entered, so it first is loaded into memory and placed on our process list, it is given the highest priority. then rule 4a says if a job uses up an entire time slice while running, its priority is reduced. So every time slice that a process is being run, it will have its priority reduced. And we'll see how this looks. I know it might be a little complicated, but we'll see how this looks on the next slide. And rule 4b says if a job gives up the CPU before the time slice is up, it stays at the same priority level. So if a job says it runs for a certain period of time and then says, okay, I'm going to wait for an input output, if this all happens within a time slice, then it stays at the same priority level. So in this manner, MLFQ approximates our shortest job first. Because if a short job enters the system, because it is placed at the highest priority, it will be scheduled first. And if it is still short, it will then finish quite quickly and it will be done. So that's how it kind of approximates shortest job first. Okay, so let's look how a process that is fairly long gets its priority reduced. So here we have a 3-queue scheduler with time slices of 10 milliseconds each. Okay, so what happens when a single long-running job enters the queue? So initially, right, following that one rule, it is placed at the highest priority. So this is all job A, for example. It is placed at the highest priority and runs, because it is the only job at the moment, it is selected in terms of round robin, and it runs for one time slice, which is 10 milliseconds. And because it hasn't finished being processed within that time slice, its priority is reduced. So it moves down into Q1. Okay. There are no other jobs, so this one still is currently going to be processed or scheduled. And once again, it runs for another 10 milliseconds and it doesn't relinquish the CPU yet. Okay, and that's because this is a long-running job, right? This job, in every case, would take 200 milliseconds. And so therefore, its priority is reduced once again to the lowest queue, or the lowest priority queue. And this is where it sits and is processed until completion. All right, no other jobs enter the system, so it carries on being processed. So this is how it would look in our queue. Cool. So now what happens if during this process along comes a shorter job? Cool. So here is a case of that. So we have an assumption where job A is a long-running CPU intensive job, and that's this like quite dark orange color, and job B is a short-running interactive job with 20 millisecond runtime. So by interactive, it means that it does input-output requests. So A has been running for some time, and then B arrives at time equals 100 milliseconds. So we can see that A has been running a long time. So initially when A started running, it would have started in Q2 like on the previous slide. It would have then degraded to Q1, and then finally it would be put in Q0, and then that's where it would sit. And now we see that at 100, this job B comes in, and because it comes in as like a new job, based on, I think it was rule 3, it has the highest priority. Okay. It then runs for 20 milliseconds in total, but remember our time slices is 10 seconds. So here we see it runs for 10 seconds and it is still being processed. So then once again, its priority degrades by 1 and it moves down. It then runs for another 10 milliseconds and that's when it finishes. So it's done. And well, now there's only this A, and A then continues. Okay, so that's what happens if a new job came along. Well, now what happens when there's input-output? So here we said it was an interactive job, but we didn't actually tell or say when this input-output occurred. Cool. So here in example 3, we're going to be looking at this input-output case. So job A, once again, a long-running CPU-intensive job. Okay, by the yellow color. I know I swapped the colors around, I'm sorry. And job B, an interactive job that needs the CPU for only 1 millisecond before performing an input-output. So here we go. That's job B. Now we see that our job B runs for, I think this is 1 millisecond, I think. Yeah, runs for 1 millisecond and then gives up the CPU to wait for an input-output, and that's why then job A is scheduled, because in this time we're waiting for input-output. Then you can note that our job B stays in this Q2 priority, and that's simply because of the rule, right? If the job gives up the CPU or actively gives up the CPU based on input-output, we won't change its priority. So that's why job B sits at the top here the whole time, because it's actively giving up the CPU. Whereas job A just uses the CPU greedily whenever it can, and that's why it never gives it up, and that's why it sits in this bottom band the whole time. So you can see how Q2 is scheduled, is processed for a little bit, waits for IO, then during that time process A is scheduled, it runs for a single time slice, and then process B is then scheduled again because it has a higher priority at that point. It runs for 1 millisecond, then waits for input output, and therefore because of its waiting, we want to optimize that time waiting, so that's why A then comes back in, and this whole cycle repeats itself over and over again until both processes are completely done. Okay, so that's quite nice. So it's quite effective in terms of optimizing for those two different metrics. Now, what are the problems with MLFQ? Well, what ends up happening is three things. One, starvation. Two, being you can game the scheduler. And three, being, well, a program may change its behavior over time. So what do I mean by starvation? So starvation states that if there are too many interactive jobs in the system, long-running jobs will never receive any CPU time. So if I go back to the previous example, what if I had like job C, right, which was exactly the same as job B? Well, they would both sit in this high priority band. And in that case, when job B is being processed and then it waits for input output, well then job C would then be scheduled because it would be in this high priority. And if job C then ran for a little bit and then waited for input output, then because job B is in the high priority, it would then be scheduled next. So it would just bounce back and forth between job B and C, and job A would never get any CPU time. And therefore it would be starved of the CPU. So that's where the term starvation comes in. And the idea here is that long-running jobs will never receive any CPU time. So that's the one issue, starvation. The next is gaming the scheduler. Well, if I know that MLFQ is a system that's implemented, what I can do is after running 99% of the time slice, I issue an input-output operation. It doesn't even have to do anything. Just because I issued it, I will then stay in the same priority. All the while I utilize 99% of that time slice. So you can actually create processes, people can design processes that do this, or users can create processes that do this, simply so that they can be processed more frequently in the CPU. And this job will then gain a high percentage of the CPU time. So what you could have is a very long running job, but every 1% of the time, just before the time slice ends, issue an input-output operation, and then you stay in the high priority. So that's called gaming the scheduler. And then the third one is, well, the program may change its behavior over time. So initially it could start as a high CPU usage process, but then over a period of time, well, then it could be a high input-output request process. And our scheduler might not be able to adjust to this change. Okay, So how do we rectify some of these problems? And that is through a priority boost. So rule 5. So after some time period S, we move all the jobs in the system to the topmost queue. So this will account for either starvation as well as that third case where processes' behavior can change over time. And the example here, we have a long-running job A with 2 short-running interactive jobs B and C. So we can see that A would be scheduled first here, and then it would drop to Q1 and then drop to Q0. And the interactive jobs would just bounce up and down. Well, they would just stay in Q2 the whole time. And process A here would never move back into our high priority band. And this is a case of that starvation, right? Where we're just going to be bouncing between processes B and C, and A will never get any of the CPU time. So what we do is we do that priority boost. So once again, process A started at high priority, then it dropped down because it was using the CPU too much, and it dropped down to this lower band. And B and C's were just jumping up and down. And then after a period of time, what we did was, well, we said, okay, let's boost the priority of all jobs and put them in the topmost queue. So here we can see that after the boosting now, we have Q2 in the upmost band, and then we bounce between the others as well. So bouncing between B and C, and then we boost A, and that's why it's popped up here. And we do the same thing over and over again. So it's the idea, after some period S, we just pop everything to the highest queue. Okay, so that would account for basically our starvation as well as the changing of behavior. How do we account for fixing the gaming of our scheduler? Well, a solution to this is to utilize better accounting, and specifically we modify rules A and B. So once a job uses up all its time, once a job uses up its allotment of time at a given level, its priority is reduced. So regardless of how many times it gives up the CPU, its priority will be reduced, and it moves down a queue. So we won't get this case of where 2 jobs will jump up and down between each other in the highest priority queue. So on the left-hand side here, we have that case, right, where process B, because it's giving up the CPU, it remains in the high priority, whereas process A, who doesn't have all those input-output requests, stays in the lowest band. But now, after incorporating these changes to the rules, we see that initially process B stays in the high priority band because it's giving up the CPU, but then after its allotment of time, we then degrade it into the lower bands, and then finally the last band. So for a period of time, it remained in the highest priority because of its input-output requests that it utilized, but then over a given allotment of time, it was reduced, and then everything remained in the lowest band. So this is one way to account for gaming our scheduler. Okay, so in this slide, we're going to be looking at some specific things that can be optimized, as well as a couple other issues. And the first thing that is optimized or tuned specifically is our time slices. So the high priority queues are given short time slices, and the low priority queues are given longer time slices. So what this means is that each queue doesn't have the same length of time for its time slice. And that makes sense, right? Because what you would think that is that, well, if you're in the lowest queue, That means you're a long-running job that uses the CPU quite intensively. So these jobs should be given a little bit more time to process. And if you're in a higher queue, well, you're the type of job that is either very quick, or you give up the CPU quite frequently in terms of input-output requests. So then in that case, well, we should have a shorter time slice for you guys. So this is one way of tuning MLFQ, by having a varying values for the time slice length. And that can be simplified to the statement here: lower priority, longer quanta. So now we see with process A and B is that initially in the high priority queues, they run for a short time slice. It doesn't finish, and then its priority is reduced. And the same thing happens with process B. Runs for a short period of time, its priority reduced. But you can see how the length of time on which they're being processed is increasing. Cool. Okay, so in terms of a specific scheduler implementation, there is the Solaris MLFQ implementation. And this has 60 queues. So in all the examples we've been in, there's only been like 30 queues, but this has 60 queues. And each of these queues has a slowly increasing time slice length, like what we demonstrated in the previous slide. The highest priority queue has 20 millisecond time slice, and the lowest has a few hundred milliseconds, so it's quite long time slice length. And the priorities are boosted around every 1 second or so. So that's how the Solaris MLFQ implementation works. In terms of like specific implementation, they have a refined set of MLFQ rules. Rule 1, priority of A greater than priority of B. A runs, B doesn't. So this is similar to what we've discussed already. If the priorities are the same, they run in round robin, A and B. Rule 3 says when a job enters the system and is placed at the highest priority, just like what we've said. And rule 4 and 5 say that once a job uses up its allotment of time at a given level, regardless of how many times it has given up the CPU, its priority is reduced. And 5, after some time period S, move all the jobs in the system to the topmost queue. So this is the actual rules that are utilized for the Solaris MLFQ implementation. Okay, so that is MLFQ. Now there's another type of more advanced scheduler, and those are proportional share schedulers. And these are fair share schedulers. So they guarantee that each job obtains a certain percentage of the CPU time. And it is not optimized for turnaround time or response time, but is still considered a fair scheduler. And one technique or one type of fair share scheduling is the lottery scheduling. And that says, well, I'm going to define this concept called tickets. And the tickets basically represents the share of a resource that a process should receive. The percentage of tickets represents its share of the system resources in question. So what does that really mean? Well, in this example, we have two processes, A and B. Now, process A has 75 tickets, and process B has 25 tickets. So tickets, remember, represent the share of a resource that a process should receive. So in this case, 75 tickets represents that they receive 75% of the CPU, and 25 tickets represents 25% of the CPU for process B and process A. So how it works is that lottery scheduling, the scheduler for lottery scheduling picks a winning ticket, and it loads the state of the winning process and runs it. So if I have 100 tickets and 75% of those tickets belong to process A and 25% belong to process B, well, 75% of the time process A is going to be running first. So let's do that example specifically. So there are 100 tickets, A has 75, so that's a range of numbers between 0 and 74. Process B has 25 tickets, and that's a range of numbers from 75 to 99. In total, 100 tickets. So what happens is that basically the scheduler picks a random ticket, right? So it picks a random value between 0 and 99, including both of those upper and lower bounds. And whatever ticket that is, whoever has that ticket, whichever process has that ticket, well, it will schedule that process next, or it will schedule that process to be run. So here we have like a list of random tickets that were drawn from the hat basically, and the resultant scheduled process. So first 63 was drawn, and you can see 63 is between 0 and 74, so that's why process A is scheduled. Then 85, well, 85 is between 75 and 99, so therefore process B is scheduled. 70, once again, is between 0 and 74, so process A is scheduled, and you guys get the point. So here we see that the more tickets you have, the higher percentage chance that you'll be scheduled. Okay, and how it works is that each time slice, basically a new ticket will be drawn. So the longer these jobs take to complete, the more likely they are to achieve the desired percentages. So initially here, you can see that, well, if we had to add up all the A's and add up all the B's and calculate like a percentage of total A's and B's, it might not necessarily give us 75 and 25% respectively. But if we had to do this a lot of times, overall it would converge to something like process A was chosen 75% of the time and process B was chosen 25% of the time. Okay, so how does this ticket mechanism work? Like, how does the operating system actually handle this? Well, there's something called ticket currency. Now, there's a slight confusing aspect here to realize, is that a user can allocate tickets amongst their own jobs, and the operating system also allocates tickets amongst processes. Now, when a user allocates tickets amongst their own jobs, it can be in whatever currency they would like. Okay, but the system then, or the operating system then, must convert that currency into this global currency, the currency that the operating system actually uses. So let's think about how that actually works. So there are 200 tickets in the form of a global currency. So the operating system, handles or dishes out 200 tickets. Process A has 100 tickets and process B has 100 tickets. Now, there's a little tricky thing here, is that user A or process A has like 2 threads. So that's why you can see I've broken it down into A1 and A2. And we're going to be looking at threads later on, but simply think of it as, well, there's two like sub-processes in process A. Now, the user allocates 500 tickets to A1 and 500 tickets to A2. Okay, the user decided this. So the user for user A or process A has a total of 1,000 tickets. But the operating system doesn't have 1,000 tickets, it only has 200 tickets. So the operating system converts this based on percentages into its global currency. So it knows that in terms of process A, it's already given or decided that process A will have 100 tickets. So you can see that, well, we know that both of these values need to add up to 100. The question remains, like, how do we distribute the tickets amongst both these threads or sub-processes? Well, then we have to look at how the tickets are distributed by the user itself. Well, if we add them together, we know there's 1,000. And what percentage of these tickets do each thread get? Well, we can see it's 50%, right? 500 over 1,000 is 50%. Or 500 over 1,000 times 100 is 50%. So therefore, we know that each thread has 50% of the tickets. So therefore, in global currency, each one should have 50% of the tickets allocated to that process. So half of the tickets of 100 is 50, so each one gets 50. Now user B only has like one thread or one single process, and we see that that user B or process B allocated 10 tickets to itself. And well, 10 out of a total possibility of 10, well, that's 100% of the tickets went to B1, right? So 100% of the tickets allocated to process B should go to B1. So that's 100. So this is kind of an easy example. So I have another one here. So here, same initial setup, 200 tickets available in global currency allocated by the operating system, 100 for each process A and B. But now this time, I've said that, well, the user allocates 500 to A1 and 250 this time to A2. Okay, so now it's not so easy, right? So now we have a total of 750 tickets, all right, and we need to find how those tickets are distributed amongst these two. So we simply take, well, for A2, we take 250 divided by 750, and that gives us 0.33. So if we times that by 100, we know that is 33%. So what is 33% of 100? Well, that's just 33, right? And what would the remainder be? Well, it would be 67. We could also do 500 over 750, and that gives us 66 points. Well, times by 100, it gives us 66.66667 recurring, right? So I rounded that up to 67. So that's how these tickets, these like user level tickets, are converted into a global currency, which will then be utilized by the scheduler in order to schedule jobs. Okay, so there's a few additional concepts that we just need to look at in terms of tickets. That is ticket transfer. A process can temporarily hand off its tickets to another process. So a process can willingly say, you know what, you've allocated me 100, but I don't want all of that. I'll just take 25 and you can take the other 75. It can actually do that, as well as ticket inflation. So a process can temporarily raise or lower the number of tickets it owns. Okay. And if any one process needs more CPU time, it can boost its tickets. So if it desperately needs more CPU time for some specific critical reason, it can inflate its own number of tickets. And it can also deflate it as well if needed. Like it doesn't really need the CPU at the moment, so it can deflate that. So this deflation could be a case of like, well, it's going to handle an input-output request, well, let's just lower the tickets because we're not necessary. Okay, so how is this all implemented? So here's an example. There are processes A, B, and C, and these are kept within the process list, right, which is simply a list of all the processes that are currently in memory. And remember I talked about how this list gives us information regarding like the state that it's in, whether it's ready, running, or blocked. Well, that list also stores how many tickets each of these jobs have. Okay. And here we can see some code. The first variable is counter, which will tell us if we found the winning ticket or if we found the winning job yet. And we have winner, which we use to get the ticket number that we're going to be looking for. So we get a random value between 0 and the total number of tickets. Finally, we have current, which is basically a pointer to the start of our process list, so it will point ahead. And you can see, like I said before, this is our process list with nodes for each job. Okay, now how do we get the winning job? Well, so we get our value, so our ticket here, and what we need to do is we need to loop until the sum of tickets value is greater than the winner. Okay, so the sum of tickets, right? So if we're firstly looking at job A, well, the sum of tickets would just be 100. If we then move on to the next, well, the sum of the tickets would be 100 plus 50. So that's what we're basically doing. So while current equals head, while current is not null, we say count is equal to counter plus current tickets. So counter will equal 100. Now, hypothetically, if we got a winning ticket of let's say 75. Okay, so say our winning ticket was 75. Now, if counter is greater than 75, so if 100 is greater than 75 break, we found the winner. Okay, and that's what would occur in this case. So therefore, our current winner would be job A, and that would be scheduled. Okay, if say our winning ticket was 275, okay, say the winning ticket was 275, we would start at current is equal to here, so we'll start here, so we'll start at job A. So counter would equal counter plus current tickets, so it would be 100. 100, is 100 greater than 275? No. So we go on to the next, so we move to the next node in our list, so that'll be job B. We come back to the top. Now counter will equal 100 plus 50, so that's 150. Is 150 greater than 275? No. So we move on to the next node again, so we move on to job C. Now we say counter is equal to 150 plus 250, so that's 150 plus 250, 400. So 400 is greater than the winner, which was 275. So therefore we break and we return our current. So job C would be scheduled. So that's how it works in terms of code. Okay, so another thing to look at is the unfairness metric. And this unfairness metric says the time the job first completes divided by the time that the second job completes. So here we're comparing if I get processed quicker than, say, another job. Okay, so one example is there are two jobs. Each job has a runtime of 10. The first job finishes at 10 and the second job finishes at 20. So what we say is the time the first job completes divided by the time that the second job completes. So our unfairness metric says 10 divided by 20 is equal to 0.5. Now the closer U is to 1 means that both jobs finish at nearly the same time. Okay, so here we have a little study in terms of our unfairness metric. So there are two jobs. Each job has the same number of tickets, 100, for example. So there's 100 each. Now, when the job length is not very long, average unfairness can be quite severe. Because what you'll get is that since each job has the same number of tickets, it's like 50-50, right? But remember when I spoke about earlier is that if we only request a few number of tickets, well, that random distribution might not converge to 50-50 straight away. It might take a little bit of time. Say I draw a ticket of process A, then B. Well, I've drawn two A's and one B, so it's like 66% chance A and 33% chance B. But over a longer period of time, so when the job length is longer, that value will converge to more like a 50-50% distribution between the jobs. So that's what you can see in this graph here. The longer the job length means that when you have the same number of tickets, you converge to an unfairness metric of around about 1, meaning that both jobs completed at the same time. The last thing for today is we're going to be looking at stride scheduling. So what this means is that we determine what we call a stride of each process. And this is basically we take some large number and we divide it by the number of tickets of that process. So this large number will be defined beforehand, and an example would be like equal to 10,000 for the large number, and then we calculate the stride for each process. So for example, process A has 100 tickets, so therefore the stride of A is 100, because it's 10,000 divided by 100. And process B has 50 tickets, so its stride is 200. So here you can see what happens is that processes with more tickets have a smaller stride. Okay, so how do we use this stride? Well, a process runs, and what we do when it runs is we increment a counter, and this is called its pass value, and we increment this counter by its stride. So if the pass value was 0, and then this process runs while we increment 0 plus its stride. Okay, and if that process was A, well then it would be 0 plus 100. And what we do is then we pick the process to run that has the lowest pass value. Okay, so in code, what does this look like? Well, current will be equal to remove min from the queue, and this is basically pick the client with the minimum pass value. We then schedule that current node or that current job, and current pass, the pass value, becomes current plus stride. It becomes the pass value plus the stride value. And we insert it into the queue. Okay, so an example of this, because I think that makes a bit more sense. So initially, we have a setup of process A with stride 100, process B of stride 200, process C of stride 40. Okay, and these columns represent its pass value. So it's that value that gets incremented each time it runs. Cool. So initially, they all have value 0 because they haven't been run yet, so they all start with value 0. All right, and we randomly pick using round robin. Okay, so it's not random, it's round robin. We pick process A. All right, and that's why who runs ? Is A. So because process A runs, we update its pass value to be 0 plus its stride, which is 100. So that's why it's 100 there. Okay, now we have 100, 0, 0. So we pick between the lowest ones, which is 0 and 0, and we choose B. Okay, that's why B is here. And we update B with its stride value, so it would be 0 plus 200. So that's why there's a 200 here. Now, process A didn't change, right, because we didn't run it. And process C didn't change again because we didn't run it. So now we have 100, 200, and 0. So you pick the lowest one, which is the 0. And we then once again update 0 plus stride, which is 40. So that's what we get there. So now we have 100, 240. Once again, we pick, well, 40, right? And we add 40 to 40, so we get 80. And that's why it's CC. And now we have 100, 280. Once again, 80 is the lowest, so we're going to run C, and we go 80 plus 40 is 120. So now it's 100, 200, 120. So you can see how we just go along updating the pass values with the stride values if it runs, and we just pick the minimum run, and that's the one we choose. So this is all well and good when we have 3 processes that all arrive at the same time. But if a new job enters, it will enter with a pass value of 0, right? And therefore it will monopolize the CPU, right? Because when it enters, it starts with 0, and this will always be the lowest value. So therefore it will be processed. And it will be processed up until a point where it exceeds like the current pass values of the other processes. Okay, so if it comes in with, say, stride 20, and we were over here, it will be chosen a lot of times before 20, the pass value gets from 0 to 200, right? So that's what I mean by monopolize the CPU. Okay, so that is stride scheduling. And those are all the different scheduling techniques that we'll be looking at for our scheduling section. I hope this all makes a bit of sense in the tuts that you'll get in the following weeks. There'll be some examples where you can, practice doing a little bit of this. Anyway, thank you for listening, and I'll see you next week.